Warm welcome to yet another discussion on GATE Electronics and Communication, network related papers. So here we are checking GATE 2013. Moving to the 1 mark question, consider a delta connection of resistors and its equivalent star connection as shown below. If all elements of the delta connection are scaled by a factor k with k greater than 0, the elements of the corresponding star equivalent will be scaled by a factor of. Right. So this is basically a delta connection of resistors, and we have to find what will be the value of individual resistors in star connection if the delta connected resistors are scaled by a factor of k with k greater than 0. Right. So we can check what is this RC. Right. RC equal to RA-RB, right? RA-RB divided by summation of the total resistance, that is RA plus RB plus RC, right? In the question it is mentioned as scaled by a factor k. So RA into k, RB into k. So that turns out to be k square on numerator, and denominator side a common k is there. So I am taking it outside too, right? So it will be scaled by a factor of k units, right? It will be scaled by a factor of k units. So answer is B. So another one related to this problem is this one, that is a delta connection with the resistance value of 3, then the equivalent star connected must have value of unity, right? That is 1. Moving to the next question, the transfer function V2 of s by V1 of s of the circuit shown below is, right? So first of all we can write what is this V2 of s. V2 of s equal to, I am marking the current flowing through the circuit as I of s. So V2 of s equal to I of s into 10k plus 1 by SC. So here 1 by S into C is 100 microfarad. So into 10 raised to 6, so 10 raised to 4 by S. 10 raised to 4 by S. So substituting here 10 raised to 4 by S, that is V2 of S. Now we have to calculate V2 of S by V1 of S. Now I am marking V1 of S. Again V1 of S is the voltage across these 2 points, that is I of S into again 10 raised to 4 by S plus 10k plus again 10 raised to 4 by S. So 2 into 10 raised to 4 by S, right? Now cancelling I of s and I of s and multiplying both numerator and denominator by S, right? Yes, and cancelling again 10 raised to 4 because 10 raised to 4 is common in both numerator and denominator. So that turns out to be 10 raised to 4 cancel, it will give S plus 1, right? S plus 1 divided by 2 plus S. So answer is D, right? S plus 1 by S plus 2. Moving to the next question, a source V S of t equal to 100 V cos 100 pi t has an internal impedance of 4 plus J3, right? Internal impedance of 4 plus J3 ohm. If a purely resistive load connected to this source has to extract the maximum power out of the source, its value in ohm should be, right? So we have to find the value of this resistance for maximum power transfer, right? So for maximum power transfer, if the load is a complex one, it must be terminated by 4 minus J3. So for it to be transfer maximum power to a resistive load, it must be root of 4 square plus 3 square, that is root of 25 equal to 5, right? So the answer is C, 5. Moving to the 2 mark question here, in the circuit shown below, if the source voltage Vs equal to 100 angle 53.13 degree volt, then the Thevenin's equivalent voltage in volts as seen by the load resistance RL is. So here we have to evaluate what is the Thevenin resistance across RL equal to 10 ohm, right? As I mentioned in my earlier tutorials, this portion of the circuit has no effect on this portion, right? This portion is given to calculate some variables which are working on this portion of the circuit, right? Here when we check, VL1 is actually the voltage across this inductor. So this portion of the circuit is given to calculate VL1. Now for calculating Thevenin voltage, we have to deactivate all the voltage sources, right? So for calculating Thevenin voltage here, that means we have to evaluate at these 2 points, right? We have to first of all remove the resistance RL equal to 10 ohm, and we have to calculate Thevenin consists of only a voltage source plus or minus 10 VL1, right? This is that source 10 VL1. So now we have to calculate what is this VL1, right? So VL1 equal to Vs, right? VL1 is actually the voltage across this inductor. So VL1 equal to Vs into the impedance, right? That is J4 divided by total impedance 3 plus J4. So here we have to remember that this dependent current source, which is dependent upon I2, is actually destroyed, because as we open circuited the terminals AB, there must not be any current flowing through this loop. That means I2 turns out to be 0. So this dependent voltage source is also 0. That's why I calculated VL1 equal to now actually a series division of voltage across 3 ohm and J4 ohm. So now VL1 equal to Vs into J4 divided by 3 plus J4, right? So that is again Vs equal to 100 angle 53.13 degree from the question, right? Into J4 divided by 3 plus J4. So the answer turns out to be VL1 equal to 80 angle 90 degree, right? Now VThevenin, VTH equal to 10 times of this value, that is 800 angle 90 degree, right? So the answer is 800 angle 90 degree. Moving to another 2-mark question. The following arrangement consists of an ideal transformer and an attenuator, right, which attenuates by a factor of 0.8. An AC voltage VWX1 equal to 100 volt is applied across WX to get an open circuit voltage VYZ1 across YZ, right? Next, an AC voltage VYZ2 equal to 100 volt is applied across YZ to get an open circuit voltage VWX2 across WX. Then VYZ1 by VWX1 and VWX2 by VYZ2 equal to, right? So this configuration consists of an ideal transformer with a turns ratio of 1:1.25 and an attenuator which attenuates by a factor of 0.8. In the first case, we applied a AC voltage of 100 volt across these two terminals, and we have to evaluate the voltage across these two terminals YZ1, right? So first of all, we can evaluate that. Now we applied a voltage of 100 volt. That means VWX1 equal to 100. As the turns ratio is 1:1.25, right? I am writing here 1:1.25. That means the voltage get amplified or voltage boosted up by 1.25. So the voltage turns out to be 125, right? So I am writing this as 125. Now an attenuator is provided which attenuates by a factor of 0.8. So 0.8 is 8 by 10, right? So this turns out to be 125 into 8 is 1000, 1000 by 1000, that is 1, right? Or in terms of the answer, it must be 100 by 100, right? 100 by 100. Next, in the second case, an AC voltage of 100 volt is applied across these two terminals. So I am marking denominator side as 100, and we have to evaluate the voltage across these two terminals, right? To get an open circuit voltage VWX2 across WX. So it is just reverse of the first case. So here first we faces an attenuator, but the signal is applied from right to left. So it gets amplified by 0.8 inverse, right? So 0.8 inverse, or denominator side I am marking it as 0.8. Next, the signal faces the transformer, which transforms by a ratio 1.25, right? 1.25 is to 1. So 1.25 is to 1 gives 1 by 1.25 is actually the output voltage. That is 0.8 times must be the output voltage. So I am marking as 0.8, right? 0.8 into the input voltage. Input voltage is again 100, right? So the answer again turns out to be 1 or 100 by 100. So the option must be, C, 100 by 100 and 100 by 100. Again in this question, there is no need of actually calculating the reverse case, because the transformer and the attenuator, right? Transformer and the attenuator is basically a bilateral element, right? Moving to another 2-mark question. Two magnetically uncoupled inductive coils have Q factors Q1 and Q2 at the chosen operating frequency. Their respective resistance are R1 and R2. When connected in series, their effective Q factor at the same operating frequency is. We know Q is related as omega L by R. As it is mentioned as it is magnetically uncoupled, there is no need of using actually the mutual inductance factor. So Q equal to omega L by R. So for the first case Q1, I am marking it as Q1. Q1 equal to omega L1 by R1. Similarly for the second case Q2 equal to omega L2 by R2. Now the combined resistance is given. Now the total Q equal to omega into L1 plus L2 divided by R1 plus R2, right? The operating frequency remains the same. That is omega L1 by R1 plus R1 plus R2 plus omega L2 by R1 plus R2. But from this expression omega L1 equal to Q1 R1, so we can substitute it Q1 R1 by R1 plus R2. Again omega L2 equal to Q2 R2, right? So the answer turns out to be Q1 R1 plus Q2 R2 divided by R1 plus R2. Option C is the answer. Now moving to another 2-mark question. 3 capacitors C1, C2 and C3 have values 10 microfarad, 5 microfarad and 2 microfarad respectively. Have breakdown voltages 10 volt, 5 volt and 2 volt respectively. For the interconnection shown below, the maximum safe voltage in volts that can be applied across the combination and the corresponding total charge in microcoulombs stored in the effective capacitance across the terminals are respectively. So here C2 is 5 microfarad and C3 is 2 microfarad. These are connected in series. The lowest of the C2 and C3 is 2 microfarad, that is C3. So the maximum voltage must drop across C3, right? So when I apply a voltage V across C2 and C3, the maximum voltage must be dropped across C3 compared to C2. Because we know Q equal to CV. C and V are inversely related, right? That means when C decreases, V must be increased. So here C3 is lower, that means the maximum voltage is dropped across C3 compared to C2. So now we can evaluate the individual voltage drops. Suppose I am applying a voltage V. Now V into C3 divided by C2 plus C3 is actually the voltage appearing across C2, right? And it must be lesser than or equal to its breakdown voltage, that is 5. Similarly for the next case, right? V into C2 by C2 plus C3 must be lesser than or equal to 2, right? That is V must be lesser than or equal to 10 volt. So we can substitute the values. V must be lesser than or equal to 5 into C2 plus C3. C2 plus C3 is 7. 5 into 7 divided by C3. C3 is 2, right? That is V less than or equal to 17.5 5 volts for the first case. Similarly, for the second case, V must be lesser than or equal to 2 into C2 plus C3 is again 7 divided by C2. C2 is 5. So that turns out to be lesser than or equal to 2.8. Right? For the last case, it is directly mentioned as V lesser than or equal to 10 volt. So out of the three voltage values, this value is the lowest value. So the maximum safe voltage in volts that can be applied across the combination is 2.8 volt. Right? Now we have to actually evaluate what will be the total charge in microcoulomb stored in the effective capacitance across the terminals. Right? We know charge Q equal to C into V. For that, we have to evaluate the effective capacitance. So C effective equal to C1 plus C2 parallel C3. Remember, this is capacitance, just inverse of the operation that we are attaining on resistance. So C1 equal to 10 microfarad plus C2 is 5 parallel 2. That is 10 plus 5 parallel 2 is 5 into 2, 10 by 7. So that turns out to be 80 by 7. Right, 80 by 7 microfarad is the unit. Now Q equal to C is 80 by 7 and V is actually the breakdown voltage, that is 2.8. So now the corresponding total charge is 80 into 2.8 by 7. That turns out to be 32 microcoulombs. Right. So the answer is 2.8 and 32 microcoulombs. Now moving to a common data question. Consider the following figure. Right. The current IS is actually the current flowing through this 10 volt source. The current IS in amperes in the voltage source and the voltage Vs in volts across the current source respectively are. Right. So we have to evaluate the current flowing through this voltage source and similarly the voltage across the current source in this question. Right. This is actually a common data question too. So we can apply Kirchhoff's current law at this node. Just applying Kirchhoff's current law at this node gives the answer. So a 2 ampere current is entering this node. So I am marking a 2 ampere current at this node. Now a current IS, that is what we have to evaluate. So it is IS. Now this 2 ohm is actually connected in this way, connected parallel to this 10 volt. So the current flowing through 2 ohm is voltage is 10 volt divided by the resistance, that is 5 ampere current. Right. Again another 1 ohm is there. Again the voltage remains same. Voltage is 10 volt divided by resistance now turns out to be 1. So here it is 10 ampere. Now entering current is just 2 ampere. So 2 equal to IS plus 5 plus 10. So IS equal to 2 minus 15 or minus 13 ampere. So only this option satisfies this minus 1320. That is answer is D. For calculating Vs, we have to apply Kirchhoff's voltage law across this loop. Right. So I am applying Kirchhoff's voltage law. Here it is plus negative. So plus negative. Right. That is 10 equal to current flowing through this 5 ohm is actually 2 ampere. So we are taking the current direction as this way because applied voltage 10 volt deliver it in this way, and also Vs is marked as plus negative. So 10 equal to current is minus 2 into 5 plus Vs. Right. So Vs equal to 10 plus 10, that is 20 volt. So anyway the answer is D. Now we have to evaluate the last question too. That is the current in the 1 ohm resistor in amperes is. That is we actually evaluated. Right. That is 10 ampere. So this is 10 ampere. So for more GATE tutorials, subscribe my channel. Now I am signing out till we meet again with another GATE paper. Thank you.